The Berkeley AMPLab was a research lab where Apache Spark and Apache Mesos were both created. In the last 5 years, these projects, Mesos and Spark, they've changed the way that infrastructure is managed, and they've improved the tools available for data science. Because of its proximity to Silicon Valley, Berkeley has become a university where fundamental research is blended with a sense of industry applications. And Apache Spark and Apache Mesos were perfect examples of this. They came out of the union of university research talent and highly applied corporate problems in distributed systems. At Berkeley, students and professors move between business and academia, finding problems in industry and bringing them into the lab, where these problems can be studied without the day-to-day pressures of a corporation. This makes Berkeley the perfect place for research around serverless. Serverless computing abstracts away the notion of a server, allowing developers to work at a higher level and be less concerned about the problems inherent in servers, such as failing instances and unpredictable network connections. Of course, there are servers in the mix. The cloud provider is operating servers to power this functionality, but the user is not exposed to those servers. With serverless functions as a service, the cloud provider makes guarantees around the execution of serverless code. This is the case with AWS Lambda, Azure Cloud Functions, Google Cloud Functions. With serverless backend services, the cloud provider makes guarantees around the reliability of a database or queuing system. Today's show centers around the serverless functions as a service. This is a new paradigm of computing, and there are many open questions. We've done many previous shows about serverless computing. Some of the open questions: how can the servers for our functions be quickly provisioned? Because these functions are going to run on servers and we want them to execute quickly. There's what's known as the cold start problem that we've covered in previous episodes. How can we parallelize batch jobs into functions as a service? If you have a large MapReduce job, it would be great to parallelize it into functions as a service so they can run efficiently and cheaply. How can large numbers of serverless functions communicate with each other reliably so that they can coordinate actions despite being these ephemeral distributed functions as a service running in containers? In today's production applications, functions as a service are mostly used for event-driven applications. They serve the purpose of being glue code, but the potential for functions as a service is much larger. Ion Stoica is a professor of computer science at Berkeley, where he leads the RISE lab. Ion is the co-founder of Conviva Networks and Databricks. Databricks is the company that was born as a result of the research on Apache Spark. Ion now serves as executive chairman of Databricks, and Ion joins the show to describe why serverless computing is exciting, the open research problems, and the solutions that researchers at the RISE lab are exploring. Before we get to today's show, I want to mention that we are looking for several open positions that are available at softwareengineeringdaily.com/jobs. We're looking for journalists, podcasters, a couple engineering interns, and also an entrepreneur in residence. If you're interested in researching a subject and potentially building a business around it, then check out that role. You can go to softwareengineeringdaily.com/jobs. We'd love to hear from you. How do you know what it's like to use your product? You are the creator of your product, so it's very hard to put yourself in the shoes of the average user. You can talk to your users. You can also mine and analyze data, but really understanding that experience is hard. Trying to put yourself in the shoes of your user is hard. FullStory allows you to record and reproduce real user experiences on your site. You can finally know your user's experience by seeing what they see on their side of the screen. FullStory is instant replay for your website. It's the power to support customers without the back and forth, to troubleshoot bugs in your software without guessing. It allows you to drive product engagement by seeing literally what works and what doesn't for actual users on your site. FullStory is offering a free 1-month trial at fullstory.com/sedaily. for Software Engineering Daily listeners. This free trial doubles the regular 14-day trial available from FullStory.com. Go to FullStory.com/SEDaily to get this free 1-month trial. And it allows you to test the search and session replay from FullStory. You can also try out FullStory's many integrations with Jira, Bugsnag, Trello, Intercom. It's a fully integrated system. FullStory's value will become clear the second that you find a user who failed to convert because of some obscure bug. You'll be able to see precisely what errors occurred, as well as the stack traces, the browser configurations, the geo, the IP, other useful details that are necessary not only to fix the bug, but to scope how many other people were impacted by that bug. Get to know your users with FullStory. Go to FullStory.com/SEDaily to activate your free 1-month trial. Thank you to FullStory. Ion Stoica, you are a professor of computer science at Berkeley. Welcome to Software Engineering Daily.
Thanks for having me.
So I reached out because I heard from Dave Patterson. I was talking to him in a podcast episode not too long ago. He said that you are interested in serverless computing, or you're working on some projects associated with serverless
like
computing.
Many others.
Like many others, yes. So serverless computing, this can mean a number of different things. What's your definition of serverless?
Serverless computing is just, for the context, why we are talking about serverless computing, right? Is cloud was, so to speak, invented in around 2006 with the emergence of Amazon Web Services. And what they provided the ability of people to, instead of building their own data centers, to spin off a bunch of VMs on the cloud. So it was much faster to get resources than ordering and receiving servers. That process takes months. And also effectively elasticity and free scaling. You are only paying for how much you are going to use these virtual machines. So that was a huge improvement compared with what was in the past, where you need to build all these the clusters and the data centers. However, what these early cloud services didn't provide you or don't provide you, or I should say what they still ask you to do, is to manage the resources. So you still need to manage the VMs to make sure that you know how many you need. You need, when you are going to be done with the computation, you need to power them down. You need to also scale explicitly the number of VMs, both up and down. So really, you need to operationalize and manage these VMs. So now what basically serverless is providing you, it's getting rid of all this operational and management overhead, right? And now to get to your questions, what I think that are the key characteristics of a serverless platform. And now every major cloud providers provide these serverless services, starting with AWS, which provides AWS Lambda, Cloud Functions, Azure Functions from Microsoft and Google. So provides you following serverless platform has the following key characteristics. First, it's basically decouples the computation from storage. Let me give you an example here. So for instance, it used to be that, or every major cloud provider also provides, say, database-like services. And in the past, that was running database instances. And there are many such examples. And like, for instance, one of the most successful is Redshift, which is a parallel database provided by Amazon. Now, with these services, you have to pay for these instances, which have both computation and storage. Now, if you do not use the database, you still have to pay for it, right? You still need to pay also for the compute capabilities of that node. What does decoupling computation from storage means? Now, take, for instance, BigQuery, which is the first serverless query engine. In that particular case, basically when you don't run a query, then you pay only for storage. So you pay for storage, which actually can be in a blob store. And then you are going to pay only for computation. You are only going to pay when you are going to perform a query, right? So this decoupling of storage from computation, it's one of the most defining features of serverless. The second one, it used to be that you have to pay for the resources, right? I am using a VM for 1 hour. I am going to pay for that, right? With serverless, you are going to, instead of instantiate a VM and installing your software and running your software on it, you are paying for the execution of a function, say a Python function, right? So you pay only for how much your function or your code is executing, instead of paying for the server on which you are going to install the code and then run your application. The last one is that when you are going to, so the last one is this capability to transparently scale up and down, right? You have more functions you want to execute, you are going to get more resources. You have no longer functions to execute, you are not going to pay for anything. So this transparent scaling up and down, which with respect to your computation demands, it's also a defining feature of serverless. It's again, in the past world, you have to do it explicitly. You need to manage these VMs, you need to explicitly scale them up and down. And if you forget to tear down or to shut off to a VM, you are going to pay for it even if you don't run anything on it. So for actually to facilitate that, typically today, all these serverless platforms, they have a timeout associated with execution of every function, right? Like for instance, AWS Lambda, they have 10 minutes now. They used to have 5 minutes, now they have 10 minutes. So this means that after 10 minutes, even if your computation hasn't finished, they are going to shut off the Lambdas. But this is also protects you as a user, because you don't need to explicitly keep in mind that, my computation now is done, so I need to shut down the servers.
Mm-hmm. So you've described a couple different flavors of serverless, a couple different examples of serverless in terms of, you gave the example of BigQuery, which is a rich query service that has both compute and storage associated with it. And you also mentioned AWS Lambda, which is more of a primitive, and it's an efficient, scalable way of executing simple functions. These are two different categories of serverless, these primitives as well as these rich computational services. Are you more excited about either one of these particular areas?
Yeah, I think it's a very good point. So, there are two types of serverless, so to speak, platforms. One is called Function as a Service, or FaaS. This is AWS Lambda or Cloud Functions, Azure Functions. The other one is called BaaS, Backend as a Service. This is more about, like I gave examples, like BigQuery or Athena in AWS, in which you are going to get a service which is, so to speak, serverless, in the sense that you do not need to be worried about explicitly allocating and managing the resources. I think that just before answering your question, is that about which one I'm more excited about. It's a continuum there, right? In both cases, notice that you decouple. In both cases, both of this BaaS and FaaS, they decouple the storage from the computation. Which means, it's again, when you are going to need some compute, you are going to pay for it. If you don't use a compute, you are not going to pay for it, right? In both cases, if you use storage, you are going to pay for it. Obviously, if you run a query engine like BigQuery or Athena, you are going to have some data and you have to store it somewhere, right? Typically in S3 or in a blob store, other storage like that, right? With the function as a service, again, if your application requires to process some data, you are going to pay for that separately. Now, what is different it's how opinionated is the framework, right? What you can execute. In one case, you have a very opinionated framework, like providing with SQL, like interface. So you just can write SQL queries, right? In the other case, so this is a this is what it's the BAS, the backend as a service. In the other case, you have a lot of more flexibility in the function as a service. You can execute any arbitrary function using some of the, in general, high-level programming languages like Python or even JavaScript or things like that, right? Okay, so that's the key difference, actually, right? Now, what I'm more excited, obviously, as a researcher, I'm excited more about things where I have more flexibility. We are going to do more things, right? So clearly, the function as a service platforms are more interesting for us.
Mm-hmm. That makes sense. Now, I find this somewhat in contrast to the work of the AMPLab, because the AMPLab was all about these resource management tools like Mesos and Spark, which really improved the programmability of infrastructure. Serverless computing takes advantage of some of these resource managers and builds simpler interfaces that are, in some ways, more restrictive. I guess you're just launching a function, but you can do anything by composing functions together with some serverless storage system as well. So there are some unsolved problems. So these serverless systems are often built on top of these resource managers, like a Mesos or a Kubernetes. There's a bunch of different Kubernetes-based serverless platforms that you can basically layer a serverless function platform that you run yourself on top of a resource manager like Kubernetes. And there seem to be some challenges in the scheduling, in the cold start problems, on top of in those serverless scheduling systems. What are the challenges that you see in building these simpler serverless interfaces on top of the resource schedulers?
Yeah, that's a great question. So, serverless initially, let me, from now on, unless I otherwise specified, I'm just going to, by serverless, I'm going to mean the function as a service. So one of the motivating examples they were introduced for was to process this kind of event-driven applications. So for instance, you have some data, some logs landing on S3 in Amazon. And when you get this data, you want to process it, to do some ETL, extract, transform, load that logs, right? And maybe push it to a database from which you can query. And the problem was that if these logs are landing infrequently, the only choice you had in the past is to have just a VM running, waiting for the data to come, right? Which was quite expensive. Obviously, you can monitor in another way whether the data is coming, and when you know that it's coming, you instantiate a VM, but instantiating a VM takes a long time, right? So for this particular use case, Lambdas was a great solution because now you have something which can be, some computation which can be triggered when the new data arrives in S3 and process it immediately, at least when you compare with a VM, right? The start time for Lambda, for a function, cloud function, is measured in seconds rather than minutes or tenths of minutes of a VM, like it was in the past. Now, once you have this kind of, obviously, it's very nice abstractions, like I'm talking about these functions. People obviously, they try to do more than what they were initially maybe designed for. And they try to do, analytics, to do, implement query engines. And here we have a, system called Pyrin, which tries to make it even more convenient to use this, the Lambdas and other cloud functions or Azure functions. And we try to do even linear algebra on top of Lambdas, right? So really trying to use it and for general purpose, parallel and distributed data processing. So now when you try to push the existing platforms, fast platforms, to this application, to these very general applications, obviously you are going to see their limitations. And each limitation, it's an opportunity for research, a challenge, right, you could address. So let me say a few of them. So right now, when you use a function as a service, typically, if you want to process the data is on S3. And if you want to run more complex application, like say MapReduce, right, analytics, you need to exchange the data between functions. right, between mapper functions and reduce functions. When you have to do that, the only way you can do today is through something like S3, right? But S3 is pretty slow. Not only it can be pretty slow, but also it has a limit of how many IOPS per second, right? The number of input outputs operation per second. So the number of files you read or write per second is limited. And also you pay for each read and write. And that can be both quite limiting in terms of performance and also quite expensive. Especially since, for instance, if you want to do a shuffle between the map and you have to do a shuffle between the mappers and reducers, you are ending up with an n-square problem, and because you need to send something from each mappers to each reducer, and each of these send, it's going to be, you need to implement it as a writing to the store and reading from the store. Right. So, and there are many other examples. So one challenge is basically to provide a much faster and in some sense cheaper store for keeping the application state. Right. We are not talking here about the permanent state, but keeping the application state with only the duration of the computation. Like, for instance, the state with respect to shuffle, which expect maybe if you do a distributed training with respect to model, right, on the duration of the computation or on the duration of the application. Okay, so that's one. The second one, which is also, it's like with Lambda, with these cloud functions, like you said, you have no control where they are located, right? It turns out that for some applications, this is a problem because the communication becomes much more inefficient. Let me give you an example. So say you want to implement a broadcast operation to send a piece of data from one function to all the other functions, right? And there are many examples like that, like you do distributed training and other, or, linear algebra and things like that. Now, each lambda, it's pretty small. It's maybe one core in general, right? So now, if I want to send a piece of data to 1,000 lambdas, 1,000 functions, I have to send one piece of data, again, storing and reading it, to every of these lambdas, right? So 1,000 times. Now, if you think about how would I do it if in the old world or with the VMs, then the way I would do it, I would buy some big VMs, which have 32 cores or 64 cores. Then say if it has 64 cores, if I have 16 such VMs, I got 1,000 equivalent of 1,000 cores, right? And then I need to send the piece of data only to each VM. So I need only to send 16 times, right? Because each VM then can distribute, or all the cores on that VM can share the data, right? So now compares sending 16 pieces of data with sending 1,000 pieces of data, right? So that's one issue, and that fundamentally because you have no control on where these lambdas are executed, right? So that's another challenge. Another one you mentioned about the startup time. Right, I was saying, a lambda, you can start it in, say, seconds, right? 1 second, 2 seconds. The problem, though, is that you start the lambda, but say you want to run some Python code. So you need to load all the entire environment, libraries. And this alone, it may take, the environment, it will be, say, can be hundreds of megabytes or even over 1 gigabyte. So just downloading this environment and libraries may take tens of seconds. So that's a problem, right? It's like, so, and here it's a challenge. There are ways to address it, like, for instance, maybe caching it, maybe, dynamically download only what you need, right? But it's an interesting research problem to work on. And finally, I would say it's about isolation and security. Right. And, in many of these cases, the lambdas they run as containers, and the containers, they provide less isolation and less security than, say, a VM. On the other hand, the fact that they can run anywhere, it's, it's a positive thing for some, it's makes them more robust against some security attacks because you cannot target them. You cannot target where the code is running. So you can just run there some malicious code to snoop on the activity, on the communication of an application.
Today's sponsor is Datadog, a cloud monitoring platform for dynamic infrastructure, distributed tracing, and logging. The latest AWS X-Ray integration from Datadog allows you to visualize requests as they travel across your serverless architecture. And you can use Datadog's Lambda layer to collect business-critical metrics like customer logins or purchases. To see how Datadog can help you get a handle on your applications, your infrastructure, and your serverless functions, sign up for a free trial today and get a free t-shirt. Visit softwareengineeringdaily.com/Datadog to get started and get that free t-shirt. That's softwareengineeringdaily.com/Datadog. Thanks to Datadog for being a continued sponsor. Now, as a researcher, so in the AMPLab, you were able to build everything from scratch. Mesos or Spark can run on your own machines or in whichever cloud provider you want. But as you start to study the AWS Lambda environment or the function as a service environment within a cloud provider more broadly, you're essentially building a set of research projects on top of proprietary material. To some degree, the AWS resource is going to be opaque, and you're not going to really know what's going on underneath it. Is there a degree to which you feel constrained in your research because of that opacity?
So, on one hand, yes, there are constraints. On the other hand, sometimes the constraints are good because it focuses your work, right? We had, even before we had constraints, right? The fact that we could only use and run on top of VMs was, 7-8 years ago, a constraint because you cannot run on the bare hardware, right? You cannot manage the hardware. The VMs also is this, obviously, interposition layer, which it takes a toll on performance, adds overhead, and so forth. So this is just the next level. I will say two things. So one is, again, it's like we are doing one is you can still address some of the challenges. Like, for instance, I was talking about providing like an ephemeral storage to fast, high throughput to maintain the application state. And so that you can still something to work on. And actually, you can deploy it in the existing, on the existing public cloud infrastructures. There are some things, like you notice, you have less control about the location of and the scheduling of these cloud functions. However, this will make you focus more on the algorithms you can design around these kind of constraints, and they are going to take advantage about other features of the Lambda, like seamless scalability. And anyway, in many cases, when you have constraints, it does make the problem harder, and some researchers like that way. But that's one thing. That's what we are doing. Again, we are building Pyrin, which is a layer on top of Lambdas, which make it easier to use and write more sophisticated application. One of these applications we are writing on top of Pyrin, it's non-Pyrin, so it's basically a linear algebra on top of Lambdas. Right, we are looking at building this kind of fast ephemeral storage to keep the application state. So that's one line of research. The other line of the research, we are also providing building full-fledged stacks to provide Lambdas-like functionality, right? And you can run that. I can run that using the existing VMs, infrastructures in the public clouds, or I can run it obviously on other data centers, right? It's private data centers. We have a system called Ray, which provides you it's bindings for Pythons, in which you can parallelize your Python code and in a simple way. an intuitive way. And, the interface resembles, so I would say, micro functions or micro lambdas. And there, obviously, we have all the flexibility to design very scalable schedulers and resource allocations, and also in-memory storage and things like that, right? And you hope that is, again, on one hand, like we can still deploy it today, and you hope that also if we have some good ideas there in terms of what you said, resource management, scheduling, and so forth, they are going to be borrowed and used by the existing cloud providers. And we always have a very high throughput dialogue with them as part of the new RISE lab, which follows AMPLab.
Right, definitely. So with Pyrin, I think Pyrin's a good example of Lambda used to make scalable cloud resources easier to use. So AWS Lambda is this multi-pronged efficiency tool in that it can lower the costs of the operations that we're already doing that might be kind of complex to do. But it's also, since it's such a low-level primitive, we can use it to make our pre-existing or the code that we're writing, for example, just Python code, more scalable, because like you said, you can basically build a layer on top of Python and create bindings that make that code naively parallelizable. So can you just explain what Pyrin is and what Pyrin does to improve the scalability of Python code?
So Pyrin, it's about the lambdas, right? You execute individual functions. Pyrin provides you the ability to, provides higher level primitives, which allow you to specify executing some function in parallel. Like, for instance, it provides a map primitive, right? So you can apply the same function to a bunch of files. And then on top of that, we implement something like MapReduce. On top of that, we implement something like, I mentioned to you linear algebra libraries. So you implement a bunch of libraries which can be used to build applications, parallel application much easier. So it's a higher level of abstraction, right? Which provides you the ability to almost transparently parallelize your application.
Right. And it also uses S3 for the stateful coordination.
Yes, S3 for stateful. Like I mentioned, many of these applications, they are using S3 for storing the data if they need to store the data. Pyrin is also using S3, but it's trying to make it as transparent as possible.
Can you give an example that would illustrate when Pyrin is useful?
Yes. So if you want to provide, if I want to process data in parallel. If I want to process data in parallel, I'm going to do that in Pyrin to with one line of code by passing the function which needs to be applied on all or a bunch of inputs. It's another way. I gave you an example. It can be used to build on top of it MapReduce. MapReduce is non-trivial to express using the current low-level lambdas or cloud function interface.
Right. And I think this relates to a paper that you co-authored last year, which was Occupy the Cloud. This is distributed computing for the 99%. And the emphasis on that paper was the usability of the cloud.
Yeah. So basically, this is, the way to think about that is the following, right? It's like, we have these frameworks to do parallel computation and parallel data processing, like Spark, which we've done here in the past. However, in order to use those, you need to deal with allocating VMs and managing them, right? So you need to have to deal with operationalizing and managing their cluster on which you are going to build Spark. And that turns out to be a high barrier, especially for non-computer science scientists, biology, physics, and so forth. Right? They didn't want to deal with that.
Right.
Now you have lambdas, or cloud functions, which you don't need to manage them. because they are just going to run the code you provide, but they have a very low interface.
Mm-hmm.
You just execute individual functions.
Yeah.
So Pyrin is trying to get the best of the both worlds.
Yeah.
To provide you a higher level interface so that you can run parallel application easily, which comes together with, while the other way to say it, while getting rid of the need to manage the clusters.
Mm-hmm.
So that's what, in some way, Pyrin is.
Right. Well, so I mean, I think there was one point in that paper that said even machine learning graduate students most of them had not run a distributed computing job in a cloud provider by the time they became a graduate student, which might seem kind of strange to some people who are working in an industry or who have worked with data engineering tools in industry for a while. And I think this extends far beyond computer science graduate students. My older brother is a biology researcher, and he has a GPU cluster that he uses like on his machine. And I told him one day, I was like, you might be able to take advantage of the cloud. And that was kind of foreign to him. And he is managing GPUs, and he thinks the cloud is too complicated to use. He doesn't know how to use the cloud.
Yes, that's exactly what it is. And the main reason the cloud is too complicated, because when you are going to go to the cloud, as this also is paid in the paper, it's not you are going to be confronted. It's not only that you need to manage, you are confronted with a myriad of choices. You have around probably more today, I think on any major cloud provider, you have, together you have hundreds of choices. What type of instance you are going to use, how big it's going to be, what kind of resources you need to have on it, what kind of storage you are going to use. It's a huge management nightmare. And then it's again, you need to instantiate the VMs. You need to make sure that when they finish, you are going to shut them down. And that's hard. Imagine that many of these machine learning tasks, when they do training, they do overnight. Before they go to sleep, they start them. But then, you need to have programmatically and, to programmatically figure out when you finish the computation to shut down the resources. That's not easy, or at least it's not trivial. While, with something like cloud function or lambdas, when the computation is done, you are no longer going to pay for it, right? Because you pay only for how long you are going to use the lambdas. So I think there are these aspects which fundamentally it's about, in the world, cloud, or traditional one, you just need to manage all these resources.
Any other areas of cloud computing that you think are too intimidating that could be simplified?
I think so. Just to summarize, one, it's about allocating resources and deallocating them. The second related one, if you need to scale them up and down, right? There are many applications which over their lifetime, they have different requirements. This is a hard problem, scaling up and down resources during an application while the application is running is hard. The third thing is just the choice. Right, you are confronted is like huge array of choices, and you don't know which one is better. Right, you need to it's just the tyranny of choice. Right, it's very intimidating. Right, imagine that you have to order a dinner and you are going to be confronted. You are going to have a menu with hundreds of items. Right, it will take you some time. It will be intimidating. It's not that experience you are going to enjoy as much, or many people don't enjoy that. The other things will be also related a little bit with the cost. People are afraid they are going to forget clusters on. Also, there is another dimension of the choice. It's, am I going to use, for instance, spot instances? Right, spot instances are much cheaper than on-demand instances or reserve instances. But on the other hand, you are not guaranteed. Right, you can lose the spot instances, and then you may lose all the computation. So all of this, I think, makes the ecosystem quite complicated, especially for someone who has never done that. So I think this is basically what it's intimidating. Yeah.
Now, this is from the perspective of the individual programmer, the individual researcher.
Of the individual programmer, yes.
Enterprises also have issues adopting the cloud or just adopting other modern technologies in general? This is something you've seen firsthand from Databricks, which you co-founded. You were the CTO. And I interviewed Matej a while ago, and we talked about Databricks Delta. We talked about some of the other projects at Databricks as well. What are the difficulties of enterprise data science? How does the enterprise usage of cloud computing and data science, is it the same thing as that graduate student struggling to figure out spot instances versus reserved instances, or are they a unique set of problems that the enterprise is encountering?
Yeah, a good question. There are two answers to that question. So one is that, say, a data scientist in today, on which, if she does not use a cloud, what he's going to use is going to use the internal resources, and these internal resources are going to be managed by the IT organization of that company. One of the main reasons these data scientists want to go to the cloud is because they want to, in some sense, bypass the IT organization, because it's again, if you need a cluster in the enterprise data center or need machine allocated, takes a long time, right? So they go there with a hope that they can bypass a little bit that IT organizations, and that they can get resources much faster, they can scale much faster, so they can run their experiments much faster. But now they have to manage it. So that's a challenge. Definitely, right? So that's one answer. So yes, for them, because they didn't used to manage, but now they have to manage at least these VMs, it's an additional things to do. There is another aspect which obviously makes the transition to the cloud maybe a little bit more challenging for enterprises. It's about security, policies, right, about where to store data and things like that. So I think that's another dimension, which although, if anything, the transition to the cloud, from what we're seeing, it's tremendously accelerating in the industry, right? It's for many, I think it's maybe a few years back, the question was if. Now the question is when.
In terms of an enterprise adopting the cloud.
Adoption of the cloud. And the question is obviously what will be the first service we are going to migrate to the cloud and so forth.
Has that made life easier at Databricks?
Oh, definitely. It's, the more people are and the more enterprises are moving to the cloud means the more potential customers for Databricks.
Yeah.
Right. And it's, again, if you think about one of the big promises Databricks is making, we are talking about this data scientist. If I go now to just Amazon and so forth, they have to manage all this cluster and so forth. One of the big features of Databricks is that it allows you to run a cluster at the click of a button. It scales the clusters up and down. So it takes away all this management and operations overhead from data scientists and lets them focus on what they are good at, to just get insights from the data, develop new models to improve the business of their enterprise, of their company, come up with new products, improve the existing products, and so forth.
Yeah, tell me more about, so you co-founded Databricks in 2013. Tell me more about how the company has evolved in the last 5 years.
Yeah, I co-founded the company in 2013. I've been the CEO for the first few years. Now I'm executive chairman. And I think that we had pretty strong vision from the beginning. We focus on the cloud. We focus on Spark, right? And I think that we always, when we look at Databricks in the past, we have this kind of plan, so to speak, that initially we are really going to focus on Spark, to making Spark successful. The second, we are going to focus on building a product, the best product for Spark in the cloud. Then to evolve Databricks in being a platform for everything being data and obviously machine learning, right? So that's kind of for the stages. And I think in the first 1.5 years, 2 years, we executed just focusing on Spark. on the open source Spark. We partner with many, and we encourage everyone to distribute Spark. So we partner with Cloudera, Hortonworks, Mapar, only to name the few, IBM later. We had close interaction with them. Then in 2015, we released our product, which provides cluster management and management for Spark, security, and a set of tools like notebooks and job execution, job launchers, to make it very easy for data scientists and data engineers to do their work on Databricks. Then we grew that business, and now it's a logical continuation. We are focusing more and more on making very easy to do not only data processing and getting insights, but also machine learning, right? And just remember that one of the first applications and one of the early motivation for Spark was machine learning. That was one of the reasons Spark was built for.
Your audience is most likely global. Your customers are everywhere. They're in different countries speaking different languages. For your product or service to reach these new markets, you'll need a reliable solution to localize your digital content quickly. TransFX is a SaaS-based localization and translation platform that easily integrates with your agile development process. Your software, your websites, your games, apps, video subtitles, and more can all be translated with TransFX. You can use TransFX with in-house translation teams, language service providers. You can even crowdsource your translations. If you're a developer who is ready to reach a global audience, check out TransFX. You can visit transfx.com/sedaily and sign up for a free 15-day trial. With TransFX, source content and translations are automatically synced to a global content repository that's accessible at any time. Translators work on live content within the development cycle, eliminating the need for freezes or batched translations. Whether you are translating a website, a game, a mobile app, or even video subtitles, TransFX gives developers the powerful tools needed to manage the software localization process. Sign up for a free 15-day trial and support Software Engineering Daily by going to transfx.com/sedaily. That's transfx.com/sedaily. So I've done some interviews recently with different companies that are working on a data platform. And this has been those two words, that bigram, is used. I've also talked to companies where it's like Uber or Airbnb, and they're building their internal data platform. And whether it's a company like Airbnb or Uber who has massive engineering experience in-house, or it's a company like Dremio that's building a data platform that's for enterprises that may not have computer science expertise, what's really clear is that this thing is really hard to build. Having this data platform that unifies all the data sources in the company and makes it really easy for the right people to have access to the right data sets and to build machine learning models productively. And it seems like such a hard problem. What kind of lessons have you learned in trying to build that unified data platform?
Yeah, I'm very happy you asked that. So first of all, what we call our platform is Unified Data Analytics Platforms, Unified Analytics Platforms, which is what Databricks is.
Right.
Yes. So going from the main motivation is exactly like you said, like you have all these companies starting, Google, Facebook, Uber, Airbnb, getting a lot of value of their data, right? And they do so by building very sophisticated platforms, right? And you have all these enterprises have also very valuable data, and everyone looks at Google, Facebook, and Uber, and which are fundamentally data companies, right? And they obviously want to take advantage of their data to improve their business, to improve their competitive advantage. But they don't have the same expertise, and they don't have even the time or to build these teams and to build the internal infrastructure, right? So this is the primary target for Databricks and companies like Databricks, how to help the 99% get advantage, get value out of their data, right? So this is what it is, right? Because it's hard. Now you are asking about lessons. I think that here, what one of the lesson is and why Databricks is so well positioned to provide an end-to-end solution to these enterprise companies. So we, even early on, we have a lot of customers buying Databricks platform because they want it. At the end of the day, they say you want to do machine learning, they want to do recommendations, they want to do root cause analysis on the logs and things like that. But it turns out that before you get to that point, it's a lot of things you need to do in trying to figure, to process the data, trying to figure out, do you have the right data? Do you have the right logs? Is the data accurate? Right? So it's, in many of these cases, they spend many months or years just on this data preparation, so to speak, phase, right? So this is what we see. So basically, you shouldn't underestimate that. And, Databricks is doing that very well. It's a bread and butter for Spark, right? So that's why it's so well positioned, right? Because many people, when try to do that, they use Spark anyway, right? And Databricks now provides the fastest Spark implementation, the most secure Spark implementation, and so forth. And we have the expertise because we are behind. Databricks is a company behind Spark. So I would say this is one thing, just never underestimate how difficult it is to prepare the data and to just understand and figure out that you have the data, you have enough information in your data to achieve your goal, to improve whatever key performance indicators you want to do. I think the second lesson, which you are seeing now more and more, is about now you are ready, you have the data, and now you start to develop models, right? In it, that process, right? Experimentation, developing models, deploying, and then learning about how they perform in production, and then going back and improving the models and deploying them again. That's extremely complicated product life cycle, right? So that's why now we are at Databricks, we are developing this new open source tool and platform called MLflow, which is trying to address some of these hard problems about tracking experimentation. So, you develop hundreds of models or thousands of models. Now, after a while, I want to go back and to understand, what parameters are good for this particular model, what data I used to train that model and things like that. Then, deploy it, monitoring the model performance in production, and then using that to improve the model, iteratively improve the model. That's emerges as one of the next level of problems you need to solve in order to really get to this promised land of turning the data into value.
Mm-hmm. So when you start working with a company, none of the big enterprises come to mind. I'm not sure what some of the customers are, but like a Coca-Cola or a giant insurance company or a bank, one of these companies that needs help, first of all, with the data cleaning process and the data organization process and sorting out how to do these things. And then eventually they're going to get to maturity and they're going to be able to have problems like, how do we roll back our machine learning models? That's a totally separate problem. How long does that take? Or are there any case studies that you've done that have been particularly interesting or that might be useful to people?
There are many. I mean, and it depends. So, there are many talks at these Spark Summits. And we have one in Europe and one in the US. This year was in June of MosCon in San Francisco.
Yeah. Yeah, I got to go to the next
4,500, 100 people. So it's pretty large. So, the short answer, obviously, is it depends, right? But we always try to focus on a particular use case. We start with a use case, right? And we help the customers to be successful with that use case, right? And because it's much easier once you see the success of one use case, it's much easier than to try to replicate it to other use cases. You ask about an example. I think that, for instance, there are two talks, maybe two examples. One is Apple, which was a talk in one of the Spark summits. So they used their problem. It's a security application. So fundamentally, they want to get logs from all their notebooks and so forth and perform intrusion detections almost in near real time, right? It's a very, large scale problems.
All the laptops in the world?
Not necessarily, not all laptops. Their own internal laptops.
Okay, they're internal laptops. Got it.
There are still a lot of them.
Right.
There is no solution out there which will, out of the box solution which will scale to the amount of data they need to process. So they use Databricks for that, ingest huge amount of data, petabytes of data, and they process this data in kind of real time using Delta and using Spark streaming to figure out the intrusion, to detect the intrusions and attacks pretty much in real time. And it's not, you can imagine that they need also, when performing the detections, they need also to look at the previous attacks to compare, to see the patterns from the past. So that's one. I think the other one, it's Regeneron, which is in healthcare, life sciences. And what these companies do at the high level, it's a very exciting area, as I'm sure you heard many times, because now they have the data to do many of these things they were talking for everyone was talking for a long time, like personalized diagnosis, personalized treatment, drug development, and so forth. And the way, at the high level, the way they do that, now they have genomics data, and you have genomics data and you combine with the clinical data and the claim data. And then you want to query all this data in order to try to figure out the answers and to give diagnosis to people. Or like, for instance, I get your DNA, I sequence it and so forth, and then I am going to check. I have libraries of mutation or variants, and I'm going to check whether you have any of those. And this will signal, maybe some of them will signal that you have a risk, right? For certain, disease, right? Then you can do, personalized treatment, right? You can compare other people which are similar to you and for which there are successful treatments, say for your conditions, and you can apply the same kind of treatments. Or you can try to figure out, like, for instance, when they do clinical trials, right? Clinical trials is very expensive. Before you can get approved, if FDA approves a drug, they need to do these expensive clinical trials. And then you want to look at all these, people you have, they are getting into a clinical trial, and you are starting to study, what the people in terms of even, DNA, the people for which they respond to the treatment they have in common, and what are the differences for people who do not respond, right, to the treatment. Right, it's a huge amount of information they can they want again a process, and for that, they need platforms to process huge amount of data to find all the similarities, so do machine learning, and and we have quite a few customers doing exactly that.
In the AMPLab, companies got started based off of Mesos and Spark and Tachyon, and these projects seem to overlap and they fed off each other in a productive way. It's clear that there was something magical that happened in that lab environment. Were there particular characteristics that you take away from that AMPLab environment that you're now applying in the Rise Lab, or that you're now seeing emerge in the Rise Lab?
Yeah, I think that there are a few things there. So first, I was lucky to have some great students, okay, like Matej and others. Ben Hinman, co-founder of Mesosphere, and Hyun Lee, who is the founder of Tachyon, now Lucio. So that's number one. The other thing I think that was our close contact with industry allowed us to understand some of the problems very early on, right? With Mesos, we understood, we seen that problem early on in how you are going to virtualize a cluster, right? Before Mesos, you have to have a cluster for your production, for your experimentations. You need to have a cluster for the real-time stack or streaming, and a cluster for data historical analysis and so forth. It was even harder, more than that, to deploy a new version, say at that time, of Hadoop. It was very serious task, right? Because there are quite a few, not always they are backward compatible, and you have a cluster which is working. How you are going to deploy? This was at the beginning of the cloud, right? So all of this was in the data center, private data centers. So you build another cluster to test a new version and things like that. You have to do that. Very complicated, right? So virtualizing a cluster was a very interesting problem and a very useful abstraction. So that's what we set up to solve with Mesos, right? And then with Spark, it's again, we are seeing firsthand how, challenges which were, people had when trying to do machine learning on top of Hadoop. And this was happening here in this lab, or doing query processing. Because at that time, I'm not sure if you remember, people started to build on top of Hadoop this Hive and Pig Latin, so to provide more SQL-like interface. And now you build that, and you have people who know SQL. Now I can query on the big data, but they are coming from these databases, which are pretty damn quick. And now you go there, and you need to wait for maybe an hour or more to get a result, right? So it's not exactly what they are expecting. It's not exactly the interactivity and they are used to, and clearly that hurts their productivity, right? So we've seen, again, this firsthand. So that was how we developed Spark. And we also said that now we have Mesos, so it will be much easier to develop Spark because we run on top of Mesos. So we don't need to build all this resource management from ground up, because this was what happening with the previous frameworks like MapReduce and so forth. You have to build all the resource management, right, from ground up. So that's one. So I think that you see that what we've done is beside great students, we are early on seeing some of the problems which are industry confronted with, and we are able to use the system we already built to accelerate the development of the new systems. Tachyon is the same. Tachyon, we are basically, one of the key, taking a step back, one of the key characteristics of Spark was in memory processing, right? This is how we are able to do machine learning much faster, because we didn't have to write data and read the data from the disk between every two iterations. This is how we are able to do interactive query processing. But now you have to write, you have this kind of cases in which you have multiple clusters, maybe a production cluster and maybe experimental clusters operating on the same data. So, but then if you have it as being two separate Spark cluster, even if they run on top of Mesos, each of these cluster instances, they need to cache the data. And it's again, memory is still expensive, right? So Tachyon was one allows them to share the data. And it's also not only that, but now the data was allocated off heap. we have certain advantages from being necessarily allocated on heap. In particular, allows us to a little bit get rid of the garbage collection overhead, which is non-trivial in Java. It also allows us to decouple the storage from the compute in the sense that now that if your computation fails, you don't lose the cache data. You just spin down, you run again the task, and the data hopefully is still there, and you can read it in, say, in Tachyon. So I think that's these are the what we are lucky to, and obviously the last thing is luck, right? You're at the right area at the right time.
Yeah. I know we're nearing the end of our time. I just have a few other questions that are kind of random relative to what we've explored so far. So the distributed systems people that I talk to, there seems to be, when it comes to cryptocurrencies, there seems to be a bimodal distribution where either they are very interested or they're not interested at all. With you, I could imagine a level of interest, but maybe it's just not in industry yet, so it doesn't really fit the thesis of, well, let's attack problems that are being encountered by industry today. What level of interest do you have in cryptocurrencies?
Less interest than I should. And when I say I should is that I've been very active in the peer-to-peer research early on. And if you think some of the technologies, and some people say it's the second coming of peer-to-peer, I think that probably it's also a matter of time, right, and priorities. I think, it's a very interesting area, but I haven't had a chance to do too much or to look into too much detail in the area.
Yeah, fair enough. What have you learned from working with Dave Patterson?
So what did I learn? A few things. Number one is you can only learn from his leadership skills and thought leadership skills. I think he is a very good organizer. He's a very good leader. He, all this we are talking about the AMPLab, we are talking about Rice Lab. These are labs which follows in a long list of labs which were started by Dave Patterson and Randy Katz more than 30 years ago. It's a very unique lab model in which, in many schools or even in industries, the labs are focused on a particular area and their lifetime, it's unbounded, at least. There is not a clear sunset for the lab. This is not true for the labs we have at Berkeley. For each lab is around 5 years. And it has a clear vision, clear goals, clear deliverables. So you can actually, at the end of the lab, you can evaluate yourself, whether you're successful or not. So this is all thanks to Dave. All of this, I learned from him. And we just try to do a poor imitation. The other thing I learned is that he is very astute and in terms of realizing what are the key trends in industry. Right. So when you are talking about the research, is that it's both the solution as a result of the problem you are working on and the trends. Right. Like, for instance, in the case of Spark, we did bet on memory because we've done some studies and we realized that a large part of even MapReduce jobs, they can fit all their inputs in the memory. Even as that, 10 years ago. But Dave was very good in it's been always good in figuring out what are the dominant trends and bet on these trends. Like now he is betting, and he bet early on specialized hardware. So I think these are the two things. Oh, and the other thing is, despite his huge accomplishment, he is still very humble in the sense, like, for instance, when he has important talks, he gives practice talks and gets feedback from graduate students. So that's what I would say. Okay.
Well, let's stop there. Ion Stoica, thank you for coming on Software Engineering Daily and being so generous with your time. It's been really fun talking to you.
Thank you. I really enjoyed it.
GoCD is a continuous delivery tool created by ThoughtWorks. It's open source and free to use, and GoCD has all the features you need for continuous delivery. Model your deployment pipelines without installing any plugins. Use the value stream map to visualize your end-to-end workflow. And if you use Kubernetes, GoCD is a natural fit to add continuous delivery to your project. With GoCD running on Kubernetes, you define your build workflow and let GoCD provision and scale your infrastructure on the fly. GoCD agents use Kubernetes to scale as needed. Check out gocd.org/sedaily and learn about how you can get started. GoCD was built with the learnings of the ThoughtWorks engineering team, who have talked about building the product in previous episodes of Software Engineering Daily, and it's great to see the continued progress on GoCD with the new Kubernetes integrations. You can check it out for yourself at gocd.org/sedaily. And thank you so much to ThoughtWorks for being a longtime sponsor of Software Engineering Daily. We're proud to have ThoughtWorks and GoCD as sponsors of the show.
Wow!